Okay, so anyway, you see you got 5 players here. We've got variables in columns. The structure is important. And you don't know how I came up with this, but I used the random number generator to grab 5 random players that matched the criteria, which is okay because I was looking for 2019 batters. So that is a simple random sample. Now, real quick, as we move on, we're about ready to do some calculations. So we need to remember our order of operations. In general, PEMDAS, so parentheses, exponents, multiplication, division, addition, subtraction. So whenever you have a calculation, whatever is inside the parentheses needs to be done first, followed by anything with an exponent, followed by multiplication, followed by division, followed by addition, followed by subtraction. So maybe what would be useful to know? Well, maybe we want to know how many at-bats are typical. So maybe we want to know a mean at-bat. Well, we can find the mean by, and you see there we have X bar, so mean X bar. If you put a bar over over the variable name, then that indicates mean. Excuse me. So to find the mean, we add together the values of the variable. So 89 plus 324 plus 0 plus 136 plus 20. And we divide by the number of observations. So divide by 5 and find 113.8. Okay. That might not be completely typical given the 0 and 324 there. So because those are pretty wildly different. And we ought to use a median that's another measure of central tendency. So we got 2 there. We can talk. Well, to find the median, we order them. So instead of having them in the order that they were in observation, we put them in order ascending. So 0, then 20, 89, 136, and 324. And 89 is in the middle. So there's your median. If you happen to have another observation on there so that you don't, say instead of 5, we had 6, you would find the mean of the 2 middle numbers. So, and the book shows you that. Okay, so we know we have a measure of central tendency here, 2 measures of central tendency here, which again are mean and median. So we know kind of an idea of what a typical at-bat is. Maybe we'll be interested to know how different at-bats can be, so how much they might vary. And the way we do that, and you can see the formula in the book, but I'm going to walk you through the process. Is you have the mean there. See the 113.8, that's the mean. We're going to subtract the mean from the observation, and then we're going to square it. So 89 minus 113.8 is negative 24.8. If we square negative 24.8, we get 615.04. And we do that for all the observations. We then add together our squared, what we call squared residuals. So 615.04. Basically just add all these up and divide by 5 minus 1. And that's the variance. So 16,760.2. The 5 minus 1 is it's a correction for using a sample. So this is the sample formula. And what we found there was the variance. It's in units squared, so at-bats squared, which is kind of hard to visualize. So what we can do is take the square root of that to find the standard deviation. And that is 129.46. So if we were to have calculated that, you can see what that might have looked like. And it's a measure of the average distance between values of the data in the set and the mean. So on average, a player will have 129.4612 more or less at bats than the mean. That seems pretty wide, especially considering what the mean was. And that might be a problematic sample. Let's take a sample of 1,000 batters instead. So again, we had the same structure. And again, players in rows and variables in columns. So we want to know what kind of, okay, well, that's interesting, but that's still kind of hard to assess what that might be. This is a cumulative distribution of the at-bats. Oh, a lot of zeros there. A lot of zeros on at-bats. What if we were to chart it here? So we can find the mean, 106.077. So that is up here somewhere. Mean would be up here. Median is this line here. So that's your 50% mark is your median. We have a huge standard deviation of 171.61. And our interquartile range, so this is the 0.75 and a 0.25, so the 75%. Is 144. Okay, so we have a bunch of values along 0. Then we also have a bunch. These are those will be extreme values right here with high numbers at bats compared to the low number at bats. So that we still might have a problem with our sample. What it is, though, we can just continue to describe it. The other measure of central tendency is the mode, which is the most frequent observation. Well, that is this one right here, without a doubt. I don't have to add anything up to know that that is the mode, and that is 0. Tail goes way off to the right of the distribution, so it's very right skewed. Well, let's talk about that for a minute. You guys have probably heard about the normal distribution before. And, it's not just that it's a more sane distribution and you got somebody over here that's a little weird. That's not what it's about. It's about the shape of the distribution. In the case of this orange distribution here, we have tails that are, if you could see this tail, it would look the same, and the weight of the distribution is its mirror image. So you could fold it in half and it would fold in on each other. That's the key there. And there are defined properties for that. I said that distribution was unimodal, meaning that there was one mode. One of the things that we'll end up observing a lot in classes is that we will have many Fs. So students who will fail exams. And usually, in my experience, this has been a higher number, but we'll have a bunch of another mode of A's or B's. In this case, probably C's. So we have one mode of just F's but a near equal or an equal number of in this case C's. But in this case, there's two modes. They're not equal, but they're really close. So this is what multimodal would look like. And this is not, as far as grade distributions go, it's not crazy. It seems to happen more often than not. And I mentioned that the skew. So the skew is a measure of, so we have probably our median is in there, and the tail goes way off to this direction. So this one's left skewed. So that's the other side of skewness. So we have, the next thing we have is we have categorical data. And I already mentioned that, but what we can do to chart that is, well, you can just count it. So in our 1,000 players, we had 46 playing for San Francisco and 43 for Seattle. You can go on down through here. And this is kind of hard to look at. So maybe we would want to have a bar plot or something like that, where we plot out the count of each type or each team. Okay. Correlation is a measure of how tightly or how well two variables move together, or actually they can move in opposite directions as well. So you can have a negative correlation, but it's how tightly they move together. You probably heard the phrase, it's causation, not correlation. And an example of that would be in the summer, ice cream sales increase. And also in the summer, swimming pool drownings increase. And there's probably a fairly high correlation between ice cream sales and swimming pool drownings. So, does that mean that swimming pool drownings are caused by ice cream sales? No. I think we can all figure that out, surely. No, it doesn't cause that. But those two are probably pretty highly correlated. We might also notice that at bats and hits, so actually getting on base, are pretty strongly correlated. Well, they ought to be. I mean, you have to be at bat before you can be on base. So there's that. But so say we wanted to actually measure that. We have the one variable we're interested in. So it's an X variable, X we're going to call it. And we have another variable, we're going to call that Y. Now, a lot of times whenever we have an X and a Y, we're saying X explains Y. That is not the case right now. We're just saying that the two have an association together. You can see the formula here. And we just, we use the sigma notation just to clean it up a little bit so that we don't have to write it out like this for every observation. But just so that we can see it, and just in case you actually had to do it by hand, you could have 1, so it's the formula, 1,000. So the number of our sample size is 1,000 minus 1. So we're doing a sample correlation. Our first observation had 31 at bats and 40 minus, and the mean was 45.877. Our first observation had 11 hits, I'm pretty sure. So 11 hits, and our mean was 14.271. So 1 over 1,000 minus 1, and then we have a parentheses here. Then we go down each row and we find each variable of interest. And and then we have the standard deviation here. So our SX and SY. So plug all those in, and we multiply these two results together, next row, and we do that on, continue to do that. So as you can see, sigma notation is a lot cleaner, but maybe not as clear. So definitely whenever you get to the homework, you definitely want to practice this so that it feels kind of normal. There's no way for me to tell you enough times to make this feel normal. You really kind of have to do it. Now, we can also plot them using a scatter plot. And here's an example of a pretty, it's a pretty strong correlation, but this cluster at 0 should be concerning. And you'll see how this kind of widens out as you get here. Well, it kind of makes sense that you would have RBI and games played. A lot of people play games and don't ever have RBIs. They may not play a lot of games. As you can see, the people that played a lot of games had RBIs. Maybe an example of a better one, of a stronger correlation. So this one's 0.96. That's a stronger correlation. It's closer to 0 or closer to 1. Still have a cluster 0, but it is definitely a more normal shape. Now, what we would, for right now, this would still be a pretty good correlation. As we get to the last 2 chapters of the class, the fact that this distance here is so much smaller than this distance here will be a problem. Right now, it's not so much of a thing to have to worry about. So this fan shape is concerning, but as you can see, it does follow this line. Now you're going to have in homework and in exams, we won't necessarily have this line here. I put the line in for the lectures so that you can kind of get used to whenever I'm looking at when I look at a scatter plot, I don't necessarily need the line to show me where it is. I usually can tell where the line is just by looking at it and kind of tell how strong the correlation is by looking at it. But right now the line is there for you guys. Okay. So that is all for today.